Okay. Hi, everybody. Welcome back. Hope you had a good couple of days. The vision students in the audience likely were struggling with CVPR submissions. For those of you not who don't work in computer vision, CVPR is the main computer vision conference. The deadline was Wednesday night, Tuesday night, Wednesday early morning. Incidentally, that doesn't generally happen, but that deadline got pushed back to today because the servers crashed, which is unfortunately fairly common for CVPR. That's what was happening at a bunch of people's ends. A couple of administrative remarks. Your homework 5 was due yesterday. Hopefully people are done with it if they're not taking late days. This was the last homework. There are no more homeworks coming. Now at this point, you should transition fully to your projects, which are due in a few weeks. The instructions for submission of the project deliverables are on the website. We will post the grades for homework 4 soon, and then the TAs will transition to grading homework 5. And that's the last deliverable. If you are in the 40803 section and you're doing all 5 homeworks, then you have no more deliverables. But for everybody else, the last deliverable is the project. Okay, so those were the administrative notes. Let's get started on the content for today. So we're really happy to have with us today Erik Wijmans. Erik is a PhD student in the School of Interactive Computing. He's co-advised by Irfan Issa and me. And Erik's been he's been doing a bunch of interesting work he started out doing 3D computer vision, did large-scale reinforcement learning, embodied AI, training virtual robots in simulation, and a number of other works in that area. And again, for context, the reason why we have PhD students and other domain experts come in and talk to you about their topics is because if you are interested in a particular topic, you should know who to connect with. And so, really, if you have questions about this sort of work, you should go chat with Erik. He's taken this class. He served as the TA for this class twice. He's extremely familiar with the material. He's a researcher in the area. So we're really happy to have him, and I encourage people to engage with Erik. And what Erik will be talking about is neural architecture search. So I know last year I ruined your intro and motivation for neural architecture search, Erik. So I won't do it this year. So I'll let you introduce what neural architecture search is. Go ahead, Erik.
Yeah, thank you for the intro, Drew. For the rest of you guys, I'll be looking at the chat, so feel free to put questions in there. I'm happy to answer questions about this stuff. Happy to answer questions. This stuff is a little strange the first time you see it, so let me know if I need to go back and re-explain something or just simply say it again. And I'll get started with the general background of what we're doing here. So kind of throughout the course, you guys have been looking at neural networks to do various different tasks. Here we have a whole bunch of images from ImageNet, so you're trying to classify what's in that image. And if we take a really high level of what deep learning is doing, and a lot of machine learning in general, is that we're trying to perform this optimization objective. We have some function f that's parameterized by some parameters theta. We have some loss function L, and some data set of training pairs x, y. And we just want to minimize the loss with respect to the parameters. And so we talk about a number of different ways to do this, like the primary workhorse here is SGD, and then there are different optimizers that are used. But the kind of constant thing that's in here, and the implicit assumption that it's not quite clear where it comes from, is this function f. And so you'll have seen different varieties of that. This is an example of a ResNet, which is a very common network in computer vision. But that network came from somewhere. And all that we're changing about it is the weights itself. The structure of it's fixed. Either you came up with it or you took inspiration from a paper. Maybe we'll try a couple different ones. But really, the structure of this function f is fixed. And so what neural architecture search is about is also optimizing over the structure of our neural network itself, not just optimizing for parameters. So you can kind of think about it of the field itself of computer vision and deep learning in general is kind of doing a human level architecture search. This is sometimes jokingly referred to as graduate student descent because you have a whole bunch of graduate students slowly performing some high level optimization on neural network structure. And so the way that this optimization works when we introduce it is now we want to minimize the parameters theta and over some set of neural networks. And this set of neural networks can be very large. So we can have neural networks that are, we can have a set of networks that has millions, if not hundreds of millions of networks in it. And theoretically, this is infinite, but for practical reasons, it'll be constrained. And so that is the general ethos of neural architecture search, is we want to look for not only weights of a network, but also the structure of the network itself. And so at a high level, how neural architecture search operates is we first define some search space of networks. That's this thing F in our optimization objective. And we'll talk about different ways to define this space later on. But for now, that space is just something that's fixed. Then there's some search method that we use to select what we think would be a good neural network architecture from that search space. We use that to generate some proposed architecture. And then we evaluate how good that architecture is based on some criteria in the function that I was talking about earlier. That would just be over the loss. But we'll see later that you need not select just based on loss. There's other ways to do selection besides that. Then the result of the evaluation method is used to refine the search method in some way or another, used to decide, did we do a good job at selecting a network or not? And then this process iterates over the course of time through hundreds and hundreds of cycles, if not thousands of cycles or tens of thousands. And then we, from this, select a best model. So now we'll look a little bit at the evaluation method in a little bit more detail.
Erik?
Yeah.
Could you back a slide? And actually, yeah, this is good. This is good. So I want to make a couple of two comments. One sort of mostly just a facetious comment, just so people understand high level picture here. Sometimes jokingly, we say that the job of machine learning systems or AI systems is to automate processes in other domains, right? If you remember lecture 1, we talked about why would you want to do end-to-end representation learning? It's because you may not understand the data domain that the data is coming from, and so you have to make minimal assumptions and learn parameters in that way. So the job of machine learning is to automate or put experts in other domains out of their job, if you will. Neural architecture search is that targeted back to machine learning. So the job of neural architecture search is to put machine learning experts out of their job, right? Like you're supposed to automate yourself out of your job. And so this is that. Why must we require human intuition in coming up with architectures? Why can't we just automate that? So that's the high level intuition. The second comment is much more concrete. If you stare at this box, there are direct one-to-one analogies to parameter learning that we have seen in this class. Search space for parameter learning is once you choose an architecture, these are parametric classes. We call them model classes. Every point in that model class corresponds to a particular parameter setting. Here, search space corresponds to architecture setting. Every point in the search space will correspond to a particular architecture. The search method for parameter learning was gradient descent. That was our basic workhorse. Evaluation was, for parameter learning, loss functions. So we're basically going to take those exact same optimization model class data concepts, and we're just going to apply them to architectures. So that's the one-to-one analogy you should keep in mind. Go ahead, Erik.
Yep. Yeah, those are useful comments connecting these back to what you guys have seen before. Okay, so in terms of the evaluation method, Generally, the way that the evaluation method works here is we do performance on held out data. So we have some train set like normal, and then you have some kind of additional validation set that you use for not deciding when is the best place to stop training my parameters, but how good of a network have I selected? So this is realized as first partially or sometimes fully training the neural network and evaluating its performance on held out data. And so this changes the objective slightly, or this is kind of similar to meta learning in some ways in terms of spirit of the objective. We're not looking for a neural network architecture that performs well on the training data. We're looking for one that generalizes well to held out data. And due to this kind of bi-level optimization objective, we're able to do that. It's easy to formulate this in a way where we train on one set of data for our parameters theta, because they're still, at the end of the day, some parametric neural network, and then evaluate the quality of the architecture on held out data. So we're evaluating the architecture's generalization qualities, not its ability to fit the training set.
Erik, so let me clarify a couple of terms that you heard there that some people may not be familiar with. So there was a term called bi-level optimization that people who haven't taken sort of advanced optimization classes may not be familiar with. Bi-level optimization are optimization problems where either the objective function or the constraints involve a second optimization problem in itself. So imagine if I wrote down min f of x such that x equals argmin of g of x. So I'm already talking about min f of x comma y. So maybe there are two variables where one of those variables is already an argmin of a second optimization. Those are bi-level optimization problems because there is an inner loop of an optimization problem that gives us an argmin, which is then used. This happens in a number of contexts, but more specifically in machine learning, it happens in what is known as learning to learn. So that's not something that we're covering in this class. We're not covering meta learning in this class, but you should know that these terms exist and their connections exist. So you can phrase them as that. Okay. Erik, there's a question that has come in. Is held out data just the test set from the train test split?
So ideally, it would be something else, like you chop up, say, 90% of your train to be the thing that you train your parameters theta on, and then you'd hold out an additional 10% of train to evaluate the architecture. In practice, people tend to use the same validation set that they'll actually finally report performance on as the one that they use architecture selection for. There's a bit of training on the test set that goes in there. That is something that's kind of just a reality of the field because it's tricky to compare against architectures that were hand designed if those get to train on more data effectively because they don't have to chop up their training set. But yeah, ideally you'd have an additional test set for architecture selection. So you'd have a train set that you use for training parameters theta. You'd have some like neural architecture set test set, some neural architecture search test set that you use for selecting the architecture, and then some final test set that you'll use once you've selected the best architecture and trained those weights to evaluate its true generalization performance on truly held out data.
Yeah, the high-level principle here is that the only purpose of test data is to estimate one number once, which is how good is my approach doing. If my approach involves learning architectures and learning parameters, whatever it involves, you get to look at test data once, and that tells you an unbiased estimator of when I ship your approach on new data, how well will it perform. If you make any decisions after looking at that one number, now you are performing a sort of minimization problem on that test set. You're not supposed to do that. Of course, the ground realities is that we all do it as a community, but that's the high-level principle, that the job of the test set is to give you one number once.
Go ahead. Exactly. Yeah, so does that make sense for kind of at a high level what the evaluation function's doing? That's this training for generalization is in general what the evaluation function is. We'll see in a little bit that you can add additional things to it, but I just want to make sure that that makes sense. Okay, I don't see anything coming in on that, so I'll keep on going. Okay, so now we'll start talking about the search methods. This is kind of where most of the work goes in, is in the search methods themselves. There is a fair amount of important work that happens in designing the search spaces. If you can figure out a search space where like a randomly drawn neural network from that search space is not half bad, that will dramatically improve neural architecture's search's ability to come up with a good network, because it has to spend less time pruning away all the bad ones. But most of the work is in the search itself. And so we'll start off by talking about search via reinforcement learning. That's where neural architecture search largely started, is using reinforcement learning for that. And we'll start by talking about this paper called NASRL. And so the general motivation for using reinforcement learning here is from the observation that a deep neural network architecture can be specified as a string of variable length. This can be done in a variety of ways. A breadth-first traversal of their DAG is a pretty common way of doing this. But so now I have a variable length string that describes my neural network, and I can have some neural network, some recurrent neural network that just outputs various different tokens in that string. And this is very similar to taking actions in reinforcement learning, outputting these tokens in that string. And so I can use reinforcement learning to optimize some different neural network that outputs what architecture I should use for my task. Yeah. And so using reinforcement learning to train some recurrent neural network to build the architecture. The way that this looks is in this NASRL paper is you have your input, and then you have just some chain of blocks that can be pretty much anything. So these operations can be convolutions, they can be normalization layers, they can be activation functions. You can add in skip connections to this. And so that gives you the ability to create residual connections, like we've seen are continually important in computer vision. So the way that this ends up looking is, so each layer in each of these operations, to add some overall structure to it, because we know that there is some structure to the way a neural network works. So we can impose that in it to make the search space easier to go through. If reinforcement learning also had to figure out what are all of the malformed neural networks, that would take much longer. So generally there's some amount of structure induced here. So each layer will be a convolution. This is for some image recognition tasks, so convolutions are a nice thing to use. And you specify in order, first the filter height, then the filter width, then the filter height, stride, and then the depth, the number of channels in that. And then in a clever way, skip connections are added to this. So in addition to having...
Actually,
yeah.
Erik, would you mind going back to the previous slide?
Mm-hmm.
So I just want to make sure people understand what's being illustrated here. The boxes in color, so the boxes in the top row, those are specifying parameters of an architecture that will ultimately be trained and tested for your particular application. The boxes that are uncolored, that is the two-layer RNN being shown at the bottom two layers, that is our architecture searcher. That is what is producing an architecture for our task. And so it can get confusing about which neural network we're talking about. So let's keep that distinction clear. And so now we've sort of, this is classical computer science, right? We've gone one level of inception deeper. Like there is a neural network that's producing parameters for a neural network, which we will train. Go ahead, Erik.
Yeah, and it gets even more confusing because in this process, we overload the word parameters because we have a neural network that's predicting like the meta parameters for a different neural network. It's not predicting theta itself. It's
Correct.
predicting the parameters that define the architecture of this neural network, not the parameters that define its output given a specific input. And so
Yeah,
there is
more specifically, we're not predicting the convolutional filters themselves, the values of the filters. We're just predicting the structural parameters, number of filters, height, stride, and things like that, not the actual values of theta.
yes, there's a question in the chat about how this differs from grid search. So this is very, very different than grid search. So something like NASRL has the architecture space for it has billions or trillions of different architectures that can be specified from it. I forget the exact constraints for each of these different filters, and I forget their maximum number of layers, but there are billions and billions of things in this space. And so searching over that entire space is like doing a grid search over the entire space is intractable. The hope is that there is some underlying structure in the space that a searcher neural network can learn to predict, can learn to pick up on. And so by having it try out random architectures in that space, essentially all of this RNN stuff is a fancy way of, if we think about the searcher as a reinforcement learning agent, all this RNN stuff is a fancy way of defining the action space for that reinforcement learning agent. But essentially, it's just selecting an architecture as an action, trying that. And then we're hoping that we can use whatever structure is in this huge space of architectures to be able to more quickly traverse the space to find a good one than we could by just trying all of the random things out. And in general, neural network architecture search does outperform grid search for very, very large spaces. If you have a pretty small space, then it's likely just worth grid searching it instead of doing something like this. But for big ones, yes, it does outperform grid search. Does that make sense?
Yeah, I'm not seeing a response, but I just want to add to that. Essentially, you should ask yourself whether the same arguments why learning parameters in a neural network is good apply here. Why do we not just do grid search by discretizing the parameters of a neural network? Because, well, there are just too many parameters. There are too many parameters, and when we discretize them, we lose a certain resolution, and the combinatorial space is too large. And our hope is that gradient descent will get there faster, right? Here, it's the sort of similar hope that you're hoping that there is some structure in that space, the space of parameters or the space of architecture meta or hyperparameters. If there is structure, then when you try various things, you get feedback, and so you do strategic trial of things. Grid search does not do any strategic trial, and that's the sort of key distinction. Yeah.
So yeah, for instance, one thing that you could pick up on there is like if you're a computer vision researcher, you'll see all the time that 3x3 convolutions are what people use instead of larger ones. That comes down to optimization difficulties for SGD. SGD doesn't do great with really large filters. And so something like this would be able to pretty quickly pick up on if I choose a filter size of 25 by 25, that isn't going to go well. SGD just can't optimize that well. And since we are trying to select an architecture that SGD can optimize well, because that's our way of optimizing the parameters, we'll quickly figure out that large filters are a bad idea. And so that would let us cut off a very large amount of the search space without trying everything else, because I know that if I make my filter really big, it's not going to go well, so I don't have to try different strides and such.
There's another question, Erik. Does this loss also have multiple local minima similar to our usual neural network, implying that we converge to locally optimum architecture?
Almost certainly it does. At the end of the day, we are training a neural network to select these architectures, and so this really just looks like reinforcement learning. Like you can use any reinforcement learning algorithm to do this, and so that will have many, many local minima So who knows if the architecture space is perfectly smooth? It almost certainly is not perfectly convex, and so there's going to be many local minima. But certainly the way that we train our searcher to search that space will have many local minima. So yeah, we'll converge to a locally optima architecture, not one that's globally optimum.
Yeah. And the distinction that Erik is trying to draw is, let's be very clear, when we do SGD on the parameters of a neural network, the parameters themselves are continuous. Here, the hyperparameters or the meta parameters are related to the architectural choices, right? Filter width has to be an integer. It cannot be a continuous value. Number of filters has to be an integer. So we have discrete optimization here happening, which is why so the actions in our reinforcement learning are discrete. And so we can't use the same language of convexity for the search space of these discrete things. We have to use combinatorial optimization language. And what is continuous here on this figure are the parameters of the RNN, which is generating these architectural parameters. And so, yes, just like other RNNs with reasonably loss functions are not going to have non-convex objectives, so will happen here.
Yep.
Go ahead, Erik.
Yeah, so skip connections here are done in a cool way. So to add in each skip connection, the network also predicts a anchor point, and these anchor points define a similarity. And so you'll create a skip connection between two layers if they have high similarities with their anchor points. So this is a nice way of adding in skip connections that doesn't require the trickiness of having the network output different numbers based on how deep you are in the architecture. You can imagine that if you're just trying to predict that I am layer n, I should have a skip connection 2 layers ago or 3 layers ago. This becomes tricky because now I have to either chop off my prediction space somehow or somehow handle the fact that different values of n create different constraints on how far back I can predict and have things still be valid. And so this is what the best architecture that this paper finds looks like. And so this looks wildly different than what you tend to see. There are skip connections going everywhere. The filter height and filter width are not all the same. In computer vision, we almost always use square filters because that just reduces the amount of things the human has to think about. It never really gets that deep. It never really gets that wide. It is decently deep, but the number of filters there is never that large. But most saliently is the skip connections. They're seemingly going everywhere, and this is certainly not something that looks like what humans tend to come up with. And then in terms of how well it performs on par with CNNs of the time. This was either 2015 or 2016 work, so it's not phenomenal numbers by today's standards, but it's on par with the time, and it showed that searching for a network is possible. This did not change the way that people come up with networks.
There's a question that I think we should just clarify. This is just to confirm. This is the architecture that was found for image classification by neural architecture search. This is not the architecture doing the search, right?
Yeah, exactly. So if we go back. So this is the architecture doing the search. You have these little blocks. It's a 2-layer LSTM, so that's why there are 2 blocks there. This is what we're doing for searching, and then this crazy looking thing is the architecture that was found.
Yeah. And so I think one thing we should keep in mind is, this is fascinating that we almost outsource this job of searching for architectures to a machine. This is what we came up with. The second thing we should do is a little bit of tempering of our expectations. and prevent the ability for us to overread into the situation. First of all, we are looking at a point estimate. In statistics, these things are called point estimates, right? You're trying to estimate the architecture, but you have no sense of uncertainty. You don't know if what you found, there are many other architectures that perform roughly the same on train test performance. You don't know if how different they are in the number of skip connections. We're looking at one point estimate that was found through this optimization. We don't quite know of the gap between local and global optimality. So we should take these with a little bit of grain of salt, but it is interesting. It is interesting that you can run this process multiple times. You can see what sort of things it comes up with. And it is interesting that it is able to match performance of some of the best architectures at that time that were designed by humans. So that, I think, is a fairly interesting result. Erik, we have another question for you. So this is how we find architectures, and we pick filters, skip connections, things like that. What about other hyperparameters like learning rate, epoch, batch size? How do we search for those with neural architecture search, or is that not part of neural architecture search?
That's not typically part of neural architecture search. I haven't seen that combination happen before, especially for these it's feasible with these reinforcement learning based methods because our reward function here is essentially like negative loss on some held out data. So we want to increase that as much as we can. So in theory, you could have that loss be not just training for a couple epochs with some fixed hyperparameters. And in terms of selecting hyperparameters for epochs, that really isn't done because it becomes quickly computationally infeasible if I have to train this network for 90 epochs on ImageNet to figure out if it's good or bad. I need to be able to train like for one epoch on maybe part of ImageNet. But we could do some hyperparameter search on top of that training procedure. Generally, that isn't done with kind of the idea being that we'll come up with some hyperparameters that are pretty good. Like there's a pretty standard set of hyperparameters that people use for CNNs on ImageNet. So we'll just use those. And then if the core ideas of neural architecture search are right, which is that we can select an architecture to kind of fit the task. And as long as we give it good hyperparameters, we can think about the hyperparameters as kind of part of those tasks. Where I don't want a network that does well just on ImageNet. I want one that does well on ImageNet when trained with this set of standard reasonable hyperparameters.
And just to add to that answer, one of the reasons why picking learning related hyperparameters like learning rate, epoch, batch size gets very tricky very quickly with sort of automated search techniques is because you should realize that something like learning rate doesn't just play a role in the first SGD update. It plays a role in all SGD updates, right? So now you have to treat your entire learning process as a computational graph. What happens in the first iteration, second iteration, third iteration, fourth iteration, I make an epsilon change to my learning rate and it affects the entire computational graph. So unrolling that entire computational flow graph and backpropping through it is just computationally intractable. Like, because what you're saying is every SGD update itself is an operation in a computational flow graph. So that's why it's typically not done. Okay.
Yeah, we could do this in the RL context, just because now we're talking about rewards. So it's just like black box environment, which is what is my loss effectively from that network. But it increases the turnaround time between giving my action to my environment, where in this case, my action is a neural network architecture specification. And what my environment does is train it a little bit and tell me how good it performs. We're increasing that turnaround time by however many hyperparameters you want to search over fold. So 10x if you search over 10 different varieties, or 100x or more. Yeah, so we'll talk about computation time in a second here. That is certainly one of the drawbacks of these types of methods.
Yeah, go for it.
Yeah, so hyperparameters for training will be different for different data sets and different initializations. So finding, like, truly given a problem, possibly a new problem on a new data set, coming up with the correct hyperparameters, the correct architecture, possibly the correct optimizer, the correct learning rate schedule, et cetera, is a very challenging task. People are starting to poke on that a little bit. There's a fair amount of work in benchmarking neural architecture search, where the goal is to have a single search method that you apply to many different problem domains to try to come up with good architectures for all of those. There's NASBench 101, NASBench 300, but this is a relatively new area of research because it's, at least in this world of NASRL, computationally infeasible unless you are Google or Facebook to do this on one task, let alone hundreds of them. But we'll talk about later on methods that are neural architecture search but are much more computationally tractable.
Eric, I think we should, in the interest of time, move on. I'll answer the question in text.
Okay. Yeah, so like we were starting to talk on a little bit, so the pro of something like NASRL is that it's a very general method. The con of it is the compute cost. This method used 800 GPUs for an unspecified amount of time, and they trained over 1,200 candidate architectures. So I don't know about the amount of time that they used here, but even 1 day, which is almost certainly less than what was used by possibly an order of magnitude, is a very, very, very large amount of compute. And so that is the downside for neural architecture search. So one way to make this a little bit more efficient, this is a paper called NASNet, is to limit the search space via blocks. And this is pretty similar to human architecture search, where, again, if we look at architectures in computer vision, you'll see that they kind of have there are these block designs, and people mostly work on the block design, and then it's about chaining the blocks together with maybe changing resolution at certain stages, changing width at certain stages. But like a ResNet, there's this residual block, and that unit is replicated many times with some minor modifications to it. But we're not trying to design a unique block for every single different layer in the network, or even if we had kind of a structure of a ResNet block, we're not trying to tune the exact width of every single filter in the entire chain. We just do it at a higher level. And so that's what this paper does. It limits the overall search space via blocks. And so this type of flow that we see here is very similar to the way that architectures tend to work for computer vision. You have some regular cell that you then replicate n times. You then have some reduction cell. This reduction cell it's not forced to do this exactly, but it will likely reduce the resolution and increase the depth. And then we have another normal cell that we replicate, so on and so forth. And so we're just going to search for these normal cells and these reduction cells, and then we'll keep them the same throughout the course of the architecture. Yeah. So we have a normal cell, we have a reduction cell, and then we replicate the normal cells n times, and we have this fixed structure where we're going to have 3 repeats of normal cells, 1 reduction, and then 1 reduction cell, and then finally a softmax layer. I guess 2 reduction cells in total. So this again is optimized in the exact same way as before, where we'll search over n and we'll search over our normal cell and reduction cell. And this is what you end up getting. This is what the normal cell ends up looking like. And again, this is the cell that is found by the searcher. This is not the searcher's architecture itself. The searcher's architecture is exactly the same as it was in the previous paper. And this, again, we see that these are not cells that we would normally expect to see. They are considerably more complicated. They have many things that are going on in them. And then this is what the reduction cell looks like. Again, it's quite complex, these cells. But at the same time, the performance of this is on par with other CNNs at the time. But But however, now we do have a benefit. They were able to find a network that uses less parameters and therefore less compute than conventional CNNs. So while this didn't increase performance, it increases parameter efficiency, which is a very important thing in certain domains. And so this brings us to a very common application of neural network architecture search, which is for looking for efficient neural networks. And that's what a lot of it centers around today. So the benefit of using reinforcement learning as our way of training the searcher is that performance need not be the only metric that we evaluate a architecture with. So this paper, instead of looking at just performance of the network, looks at two things. It looks at both the training accuracy of it. So again, this is performance on our held-out-validation dataset. But now we have this additional block of it, this additional thing in a now multi-objective reward, where we're going to take the neural network architecture that's been proposed by our search process, and we'll run inference on it on many, many, many different mobile phones, and report the latency of that inference time, the average latency there, as an additional objective in our optimization process. So we want to find an architecture that performs well on new data, but also is able to be run quickly on a mobile phone. And this is a tricky thing to do for people. Mobile phones, especially if we look at the world of Android, where you have tons and tons of different manufacturers, tons and tons of different chips. It's very complicated to know exactly what the bottleneck will be when running inference on something like a phone. Yeah. Yes, indeed we are. Yeah. But so these constraints and these varieties in hardware for mobile phones makes this a good way of doing it, because you can run into bottlenecks that are just the sheer number of floating point operations per second that the phone can do. But there's also memory bandwidth and many other things that kind of muddy the water and make it tricky to figure out whether or not a architecture will run quickly or not. Hmm. There's a question in the chat about recursively building an architecture, starting from a simple one to a more complex one. I haven't seen anything like that. There very well could be, but I haven't seen that in particular. So this general idea of looking for efficient neural networks with NAS, this works very well. So this is a plot of performance on ImageNet versus latency time on something like a mobile phone. And so MobileNet was and is what people were using at the time. And it's something that's been designed by humans to work efficiently on a mobile phone. And you can see that by searching for the architecture, you find something that is both faster and more performant. Yeah, sorry, I saw something on the chat there, but no, we are good. Okay, so that is a primary application here, and so now we'll start talking about a different way of search. So we've been talking about search via reinforcement learning, and while that has the benefit of allowing for an easy way of doing multi-objective, it has the downside of being very computationally costly. And so this is now we're going to talk about a method called DARTS, or Differentiable Architecture Search. And this is a way of dramatically reducing the computational costs by figuring out how to backpropagate through this architecture selection process. So then we can train it just like normal SGD, instead of needing to select an architecture with a searcher and run that through training to figure out how well it does. Now we can just kind of have a global loss function that both encompasses the structure of the network and the parameters, and optimize that directly. So the way that DARTS works is given a kind of fixed structure of the architecture. So DARTS won't exactly optimize over the structure of it. We can't add blocks, although we can effectively remove them. You have this general block-like structure, and the blocks are numbered, and we'll have connections in between all of the blocks where a lower numbered block has a connection to a higher numbered block. And so that'll let us do various different things like skip connections. You could also just have a linear neural network with no skip connections via this structure. And the goal of darts is to figure out what should we put for each of these dashed arrows? How should we connect these two different blocks together? And anytime that there are multiple arrows coming into a block, we'll just sum all of the different things coming in. So this is done by initially proposing a bunch of different candidates that we could have to select the blocks. These candidates can be pretty much anything. For this example, I'll just give these some particular names. So we'll have the blue line be a 1x1 convolution, the green line is a 3x3 convolution, and the red line is just an identity function. So that's what would let us do a skip connection. In reality, we'll have way more than 3 lines. That'll also include things like a no-up connection where we'll effectively sever it. And activation functions are somewhere in here. Sometimes those are on a connection. Sometimes those are just inherent to the block, where we'll sum everything and then do an activation on it. And the objective of darts is to figure out the strength of the connections for each of these blocks. Figure out the strength, how useful each connection is between the blocks. So that's the general idea, is to figure out those connections, the strength, and then to do inference, we will only select the strongest connections. So we'll train this at some training time. Then when we want to finally deploy this, we'll get rid of everything that's not a strongly, we'll get rid of everything that's not the strongest connection. How this is formulated as an optimization problem is as follows. So each of the connections is associated with some weighting alpha, and these determine how strong that connection is. I am showing just 3 alphas here, just on one path. In reality, there would be alphas for all of the different ones, but that gives you a lot of different things to look at, so we'll just look at these ones. Then these alphas are used to decide the connection weight through a softmax. So we'll exponentiate the alphas, divide by the sum of all their exponentiations to get essentially some probability function, some weighting for that. And then the output, so what goes in to block 3 from block 0, is now the sum, the weighted sum of all the different connections here. So we'll sum up our first weight times the 1x1 conv, our second weight times the output of the 3x3 conv, and our third weight times just the output of the identity function. And so then this is formalized as a optimization objective that looks like this. So we still have our general idea here where we want to select the architecture that minimizes loss on the validation set. And now again, we have this bi-level optimization idea where we want the architecture to be set to minimize validation loss for the parameters that minimize training loss for that architecture. So this is similar to what was being done in the reinforcement learning case, but now we've come up with this way to make this differentiable. Although at least written like this is computationally infeasible to get through. Yeah, so that's the objective for the alphas. And so then this objective is what changes their strengths here. So throughout the course of time, optimizing this objective will have some alphas be large and some alphas be small. And that will decide which connections get severed and which ones stay when we take the inference when we take the architecture out of training and put it into deployment in one form or another. Does this, Drew, do you want to hop in? And also, please ask questions about this. This is a fairly complex thing.
Yeah, just I want to add a couple of comments here while people are still processing. At a high level, we're trying to convert architecture search into a continuous differentiable problem, right? How are we going to do it? Well, instead of proposing new components in our computational flow graph, let's tweak the flow of data between existing components in a computational flow graph. So that's the high level bit here. We already have all the components that we want in our computational flow graph. We're just going to tweak the flow of data, right? So that's a high level idea. That's what alphas are controlling. Alphas, therefore, are continuous and therefore are differentiable. Sorry, not therefore. Every continuous function is not differentiable, but in this case, yes, they are. Also on the second point I want to mention is also on the slide is now a very concrete instantiation of what a bi-level optimization problem looks like. There is an objective function on the top, which is minimization. That objective function is written with respect to certain constraints, that those constraints themselves involve a second optimization problem. You can think of this as an iterative process if you want. First, we pick an alpha, then for that alpha, we go and solve that inner minimization problem to get theta star, and then we perform an update on alpha. But what you're imagining when I say those sentences is a approach for solving this problem. That is not the definition. The definition is as stated. So, and there may be multiple ways of solving this problem. And so this shows up very naturally in meta learning or architecture search problems. Inner optimization is solving training. Outer optimization or the objective is solving validation, which is kind of what we want. Okay, go ahead.
Yeah, so Drew was touching on slightly how do you optimize this thing. The way of actually coming up with the true solution for this is a NP-hard problem and cannot be solved in any reasonable amount of time. So instead, we'll use some approximation to it. So the quantity that we need to figure out in order to update these alphas is the gradient of alpha with respect to the validation loss conditioned on alpha. That can be approximated with kind of a one-step approximation here, where we'll take our parameters theta, we'll perturb them a little bit by looking at the change in training accuracy with respect to theta, and then differentiate that new architecture with respect to alpha on, again, the validation loss. This is a useful approximation of it, is a good way to do it. It adds computational costs because now I have to update my architecture, then run inference on it again, and backprop with respect to alpha. And in practice, this just gets approximated by taking the gradient of alpha on the validation set with respect to wherever our parameters are currently. Yeah, let me quickly read the question that popped up, and we'll see if it makes some sense or no.
Yeah, while you process that question, Erik, I'll comment a bit on this slide. I think it's important to understand that step number one is what we care about. If we could take a gradient with respect to the optimal setting of thetas, we would move in this alpha in that direction. That is hard. We can't do that. So what we're going to do, the first to second line is just doing a very gross approximation that how do we find theta star? Well, we just start from theta and take one step in the direction of the gradient. One is enough. That's what's happening. That's why it's just theta minus gradient with respect to theta of L train. And that's, it's like saying if I just ran SGD once, I will find theta star. That's a fairly gross approximation. And the third is just saying, so in order to compute the second, you would need gradients of gradients. And this is where a number of higher order gradient or derivative libraries come in. And the third is essentially just dropping that term altogether, that we're not even going to take one step that we'll figure out how to update theta later on. Okay. Erik, do you want to address the question that was asked on Q&A?
Yeah, so this is a question about kind of thinking about there being two different types of optimal architectures. You can think about an architecture that performs well once the parameters are trained versus ones that perform well with random parameters. One, of course, makes sense. That's what we're talking about here. But two is an interesting idea. I'm trying to think of. There are some connections for it. I'll talk a little bit about a paper that performs neural architecture search solely by selection. They come up with some selection function that has to do with the expressivity of a network. And so that's somewhat similar here, where we're not going to train anything at all. We're just going to, yeah, that actually is quite similar, where instead it's not performance on validation data with random parameters. There's a different way that they use to express how good a architecture might be without even needing to train it at all.
Yeah, and that's related to a paper that we gave the students to read earlier in the semester, where how well do models perform if we don't even train parameters, we just take random parameters. Yeah, so
Yeah.
should.
Yeah, and there's the randomly wired neural networks paper
Yeah.
from ICCB 2019. Yeah.
Yeah. So I think fundamentally it comes down to what are you willing to do at test time, or well, meta learning test time? Are you willing to train the networks a little bit, or do you think you deploy them? And I think the deploying just randomly is an interesting scientific question, but I don't think it shows up in any application. I think we haven't reached the stage where we believe that there are architectures for which we can actually deploy and get good performance without doing any training.
Mhm.
Erik, I just want to flag there's about 17 minutes or so remaining. So we should.
Yep. Yeah, we're perfect on time. We're just about to wrap up darts, and then I'll touch a little bit on this selection paper. Yep. Okay. So darts, this method of differentiating, trying to figure out how to do some continuous relaxation on our discrete problem of selecting our architecture, performs really quite well. It is better than or on par with existing neural network architecture search methods at the time. This was a 2019 paper or a 2020 paper, so this is fairly recent. And it does all of that with very little computation cost. So this is one GPU for one day. So this is now very much in the realm of actually feasible for people to use and experiment with, compared to NASRL, which was 800 GPUs for some unspecified amount of time. And then this is the cell that darts comes up with. Overall, again, we'll have some cell structure that will repeat instead of trying to optimize the entire neural network throughout. And so this is the cell with it, and you can see the little blocks 0, 1, 2, 3 that are determining what things go in, and then these are different activations. The C subs are the the outputs of the two previous layers. And so again, we'll have the ability to do skip connections across, and we can do skip connections kind of within the cell itself. And again, this is an overall trend that what neural architecture search comes up with generally is very different than what humans do. But it tends to perform on par with what people are doing, and potentially a little bit better depending on the specific domain. Darts doesn't have the ability to incorporate a latency objective, but if you train a pretty small network with darts, the kind of thing that darts trains is referred to as a supernet, where it is a network of networks effectively. If you train a pretty small supernet, you'll end up with a pretty small network at the end of the day. And so things like darts do perform better than people typically in that regime of small neural networks, where you can't just make the network really wide and really deep and then train it on a lot of data and have that do what'll work well. Then have that figure out what'll work well, of just having a big expressive network. Finally, we'll touch on this idea of searching via scoring, but before I do that, I just want to see if there are any questions about darts before I wrap that up.
I'm not seeing anything.
Yep, I'm not seeing anything either. Okay, I'll keep on going. So in the search via scoring specifically, it's without training. And so this is a paper called Neural Network Architecture Search Without Training. Effectively, what we're doing here is it's an idea that you can approximate how well a architecture will do once it's fully trained by determining the flexibility of the network. I'm not going to go into the details of how exactly that's determined. It's a fairly complex thing to decide that flexibility. And there's some interesting underlying math of how that works. So if that suits your fancy, certainly go read the paper. It's quite interesting. And that flexibility can be determined without training. So I can just select an architecture. I can run this flexibility decision function on it, and then decide whether or not it is a good architecture that's going to do well. And these are plots of how this function that the paper proposed works. So you have score, which is this flexibility function, its output on the y-axis, and then on the x-axis you have a validation accuracy on some task. And you can see that these things are you can see that on these three different tasks, we have CFAR 10, CFAR 100, and ImageNet, a smaller version of ImageNet to make it tractable to train this many neural networks. You can see that it's generally a x equals y line. As the flexibility of a network increases, so does its validation accuracy on ImageNet. And so this lets you evaluate hundreds and hundreds and hundreds of different architectures very quickly, because all you have to do is compute this flexibility. You don't have to actually train the whole thing. And while that flexibility isn't super cheap to compute, it's certainly much faster to compute than training. So now I'll go ahead and wrap things up here. We'll be done a little early, it looks like. So what we've been talking about here is this idea of neural architecture search, and that focuses on finding highly performant network architectures. It doesn't focus on determining weights. It focuses on the structure of a network itself. The biggest use for this is likely Google's AutoML project, where this is something that's designed for people that are not machine learning experts, that are not deep learning experts, to have some data set and have a architecture be selected that works well on that data set. This means that you don't have to figure out what architecture should I use. You don't have to read through the literature and see, for this specific type of image classification problem, what do people tend to do. The idea here is that you can just give this data, and it will spend a bunch of time crunching numbers to figure out what neural network architecture structure works well. And this is something that's being continually pushed and continually improved on. And so searching for these things it's commonly done with either reinforcement learning or gradient methods. Gradient methods have largely taken over within the literature due to them being much cheaper to compute. So more people tend to work on those because it's computationally feasible. However, the large companies are still doing a lot of reinforcement learning based methods, because that allows you to do this kind of multi-objective optimization where you both want things to perform well and you want them to be efficient in one way or another, be that memory efficiency or latency time. Yeah, so there's a question in the chat that is about the darts paper. So the darts paper trained effectively. The way that darts work is we no longer have two separate phases as explicitly between network selection and network training. We now have a single optimization problem that does both network selection and network training within it. And the way that that's realized in practice is you do alternating optimization, where you'll take your derivative of alpha, which is kind of your structure derivative of the network, and update the structure of it for one step. Then you'll use that structure to take the derivative with respect to the parameters and update the parameters once. And you alternate back and forth between these two different things. And that lets you approximately solve these complex bi-level optimization objectives.
Erik, would you actually mind going back to that slide? I think it's good for people to just have that picture in front of them.
Yeah, let me go ahead and do that. Yeah. So you have You have this single optimization objective, which is solving for both structure and parameters. So you are training the parameters of the network. And we have this kind of crude approximation of our structure derivative. That's the gradient of alpha with respect to the loss on the validation set. So we'll use that derivative to update the structure once, and then we'll compute the derivative of the parameters on the training set and use that to update the parameters once. And then we'll go back and forth between these two things. Does that make sense?
So, and if I can add some more context, in a way, it might be even worth, like if you did not know this lecture, if you did not know neural architecture search, if I just came to you and I said, I've designed an architecture, it has these multiple data traversal paths, and I have I might have called it an attention layer in between that is suppressing some paths and elevating some paths. This looks a lot like a single architecture with certain parameters that, for alpha, you go to a data set 2, and for theta, you go to data set 1. They happen to be train and val, but that's like, if you didn't know about neural architecture search, this would look like just training a single architecture. The only part that makes it neural architecture search is that you will, after you're done, you do actually want sparse connections between the data flow, and that's what you're interpreting as that single architecture that you found. But ultimately, where we've converged on is that we are going to train theta and alpha parameters together, and so there is no two-stage process. We're just going to do a single-stage thing.
Yeah, that's a good connection to attention. These alpha parameters are very similar to what you'd see with an attention mechanism. The only difference here is that kind of the weights are not a function of the data anymore. Alpha is a fixed number, and no matter what image I put in, alpha is always the same. And so they're just kind of free parameters that don't depend on the data. Instead, we're trying to set them to be performant no matter the data.
Yep.
Yeah, there we go. Jump along back to the summary. Yeah. And so one quite fruitful use of this is of these neural network architecture search methods, especially the reinforcement learning based ones, are in searching for compute efficient networks. I think so. I was showing a slide earlier with MobileNet v1 and MobileNet v3. So in v2 MobileNet, there are more versions of it, v3 and v4. Both of those have been searched for with neural architecture search. And that continues to be the path that people are taking for neural network architectures that are really focusing on deployment for mobile phones, just due to the complexity of how exactly latency time interacts with the structure of a neural network. That's a very complex thing to do and figure out. It's not as simple as trying to reduce the number of parameters or trying to reduce the number of floating point operations. There's many complexities there. Yeah, and that's all I have for you guys. I'm happy to take some additional questions.
Yeah, thank you, Erik. So there's a question about slides. Yeah, we're happy to share Erik's slides at the end of it. I just want to add a couple of high-level remarks. I think Erik's comments about Google's AutoML are very well placed. I think you should sort of keep in mind that I want you to imagine a scenario, right? Like imagine a machine learning system actually being required in a particular business requirement. Like imagine either a startup that's doing something in the online, furniture sales space or something, or a startup that's trying to analyze medical images or something. They maybe don't have the in-house expertise to train models. Maybe they have data and all they want is, is this phenomena happening in my data or not? They go to a particular large vendor like Google for their cloud computing resources, and they say, okay, can you also help me with my machine learning needs? Now, at that point of time, the way this works is like a sort of non-machine learning expert can point them to their existing offerings, and different domains require different things. So AutoML type tools play the role of not requiring a domain expert or a machine learning expert in the loop. You just point to a particular data set, multiple architectures get tried, you sort of get something that works well for your data. Automating the train process and the test process. Now you sort of have a model that can be deployed. In most of these realistic deployments, once you actually ship a product that's using machine learning, the kind of data that you get changes, and so over time you have to keep repeating this loop. So that's why you need these things in the fly, and maybe architectures will need to change as well. So that's how I want you to think about realistic deployments of machine learning systems and the role that neural architecture search will play there. Okay. There's a question, Erik. Am I right in thinking that network pruning seems to be connected with neural architecture search? So has that been done? Has anybody looked at pruning in the context of, and I think the Dart stuff can be viewed as a particular pruning of this, gigantic mega network. Have other connections been made between network pruning and neural architecture search?
Yeah. So the connection to pruning is quite interesting. I haven't seen one where people are also throwing a network pruning step into the process of training as part of your training process to figure out whether or not the network works well. But kind of at a high level, they're quite similar. So network pruning, what people are typically trying to do is take a dense matrix multiplication. And so you have a dense weight matrix and you're multiplying that with some dense activation matrix. And you're trying to sparsify that weight matrix such that a sparse matrix multiplication, you can typically do that faster because there are less numbers to crunch and less memory lookups to grab those numbers. And neural architecture search, you're kind of trying to in the space of all possible ways to design a neural network, you're trying to prune out all of the different parts that make it bad, for lack of a better term. First, and that interpretation works for darts because you do have every single possible connection instantiated. For these RL methods where you're just kind of predicting a string that is a network, less so. It's more like taking an action where you're selecting the network out of the possible space, less trying to prune out the good network from the highly overspecified bad network. Trying to think also if people have tried neural architecture, pruning with reinforcement learning. I know that pruning is commonly done with gradient-based methods like darts. You can also have a mask on your weights and differentiate into that to figure out what weights you can afford to get rid of.
Okay. I'm not seeing any other questions come in. We can hold on a few seconds in case someone is still typing. But if not, we'll thank Erik and we'll end here. So we'll wait a few more seconds. Okay, let's stop here. Thank you, Erik, again. People are welcome to reach out to Erik if they have questions on neural architecture search, on reinforcement learning, embodied AI, those kinds of things. Next lecture is when we're transitioning to the last sort of topic / module in this class, which is on unsupervised learning and generative models. So we'll cover variational autoencoders and GANs, and that's it. We have a few lectures left, and that'll be the end of the last thing that we teach you. We do not have any homeworks covering that topic because the homeworks are behind us, but we still think it'll be valuable. All right. Thank you again, Erik, and see you everyone later.
Yep. Thank you for having me.